All right. So, hello, everyone, and welcome to the 2026 Statistically Speaking webinar series, which is brought to you by the Data Science and Analytics for Precision Rehabilitation, or DAPR Center, and the Reaper Rehab Training Program, both of which are funded by the Eunice Kennedy Shriver National Institute of Child Health and Human Development. This webinar series is really designed to equip rehabilitation researchers with principles and phase-appropriate approaches to sample size planning. So over the course of the year, we're going to talk about, feasibility and pilot studies through to clinical trials and effectiveness research. We want to sort of introduce some statistical theory, methodological best practices, and of course, real-world constraints that all can be leveraged to try to improve our study design and quality, making findings more interpretable, and generally trying to improve the cumulative impact of our science. Ultimately, we want to support people in doing more credible, efficient, and reproducible rehabilitation research. So my name is Keith Lose. I'm one of the leadership team members for both Dapper and Repro Rehab, and I'll be the moderator for this webinar series. Our guest today is Dr. Ryan Polig. But before I introduce Dr. Polig, I just want to remind everyone to please mute your microphones. They should be muted when you come in, so I guess maybe please don't unmute your microphones. Um, in the event that someone is unmuted, please don't be offended if either Octavio or myself administratively mute you. We're not trying to be rude, but just to make sure the webinar can function, we'll have to do that. And as a reminder, for the first part of this presentation from Dr. Polig, if you have like a clarifying question, feel free to drop that in the chat, and I can try to like ask that at a good time that comes up. But otherwise, we will have a separate question and answer session at the end after Dr. Polig has finished his presentation. The initial presentation will be recorded, and then we will also be posting that to the Dapper YouTube channel later. And then after the presentation, we will stop the recording to open the floor for the Q&A with Dr. Polig. When we get to that point, if you've got more substantive questions, please, virtually raise your hand in Zoom, and then I or Octavio can kind of call on people to ask questions one at a time. Alternatively, that you can also still keep posting questions in the chat if your signal's bad or if you're shy about asking it, and I or Octavio can ask Dr. Polig that question. So without further ado, please join me in welcoming Dr. Ryan Polig, who's an associate professor and director of biostatistics at the University of Delaware. I also know his work from a large number of trials of varying phases in rehabilitation science. So it's a real privilege to have him come and talk to us today because we have somebody with a unique statistical expertise, but also a very unique expertise collaborating with rehabilitation scientists. So with that, Ryan, if you want to take over and start sharing your screen.
All right, hopefully we're good to go.
Sounds good.
All right, so this is sort of an informative. I'm going to lecture at you for a little while, and then hopefully we'll get into some good conversation at the back end. So I want to thank everybody for inviting me, and of course the generic title of what is statistical power and introduction to sample size planning. I did not have a more creative one, so I just went with what Keith suggested. The other thing, if you don't give these often, is you just make the first slide about yourself, and then you can't be wrong, at least for the first 5 minutes. Right, so who am I? I am a biostatistician at the University of Delaware. My background is in psych as an undergrad and then research methodology from Pittsburgh. And for people who are unfamiliar with that, that is essentially an applied statistics degree, but in education. So quantitative psychologists, econometrics, biostatistics, these are all different ways of applying statistics to a field. And that's sort of my background. So I joined Delaware in 2013 as a staff member, and I've been there since, and so sort of worked the way up and am now faculty in the epi department, and I direct the biostatistics core, but the bulk of my job is actually to be a biostatistician on applications and working with people for publications. So why am I relatively qualified to talk to you guys? So I actually started rehab research when I was in graduate school working with people in SHRS at Pitt. A lot of the individuals doing telehealth with wheelchair seating and biomechanics for training purposes. And then I have just sort of not left the world of health sciences. 13 of the 35 grants that I'm sort of on or have been on are directly for rehabilitation. Some of my most common collaborators are Darcy, Karin, and Greg, who work on post-stroke rehabilitation, Achilles tendinopathy, and low back pain. So sort of since coming to Delaware, those are sort of the main individuals I work with for rehab. Again, that's just sort of the PT department. There are other departments in the university, so I do a whole bunch of other stuff too. I've reviewed for the VA for the rehab research and development. So that's sort of like the VA's version of an R01. And I typically do about 15 to 17 grants a year to NIH. And I mean by that is R01s, R21s. I don't mean Fs. There's probably a lot more if I started including all the smaller stuff. So again, the first part of the first lecture here is going to be trying to get everybody on the same page for what's coming down the line. And so I apologize if you have recently had statistics courses or if you know all this stuff, but I want to make sure that sort of everybody's on the same base level. It's like when you're teaching a course, an advanced topic, if you always start with what the previous section should have covered, it helps catch students up. So what is a scientific hypothesis? That's a testable explanation for a phenomenon. And that's sort of, we're going to start globally and then we'll narrow in and then we'll sort of circle back to that at a point later. So within that, let's talk about statistical hypotheses. And here's sort of how I define these terms throughout the next couple of slides. They are not necessarily official ones that you would find in a textbook. I often find intro textbooks sort of limit them to be conceptually easy, but not necessarily fully sufficient. So like I would state, the statistical hypothesis is an operationalized claim that's evaluated using data. And so that means that everything is a priori defined, and we're using data to help validate the claim or support your claim with evidence. And now we'll start talking more specifically about what you guys probably thought the talk was about, which is null hypothesis testing. So the null hypothesis states that in the population, there's no effect, no difference, no relationship. The model does not fit. Counter to that is the alternative hypothesis, which states that there is effect, there is a difference or a relationship in the population, and our model does fit. And the model fit I'm using in the conceptual senses that the model that we've outlined or described or defined is a reasonably accurate way to describe the data seen. So if you think about model fit here, I'm thinking sort of in the SEM realm that we are able to reproduce sort of with a hypothesized pathways what is actually seen in the data. One thing you'll note is the statistical hypotheses themselves are mutually exclusive, so they can't both be true, and they're exhaustive, so they cover all possibilities. And we can evaluate this with null hypothesis testing. One thing I do want to sort of point out at this point is we've really conditioned ourselves to like yes, no answers in science or this, that. And so even the whole idea of null hypothesis framework, we want to come to a certain conclusion about a study. My guess is in the long term, we're going to find out that this is probably not the best way of doing science moving forward. But it's sort of where we're at now. A couple more basic terms to get everybody on the same page. You'll notice that when I defined hypotheses, the alternative and the null, I stated them in terms of the population. And that's what we really want to get to is the population. But we don't typically have the ability to measure every unit in that population. You can't sample everybody, right? There's always constraints. And so we define the population as the universe or events of individuals that you want to investigate. And that's what we want to generalize to. That's what we want our results to apply to. But what we normally can do, we can't have everybody, so we take a subset, which is our sample. And this is the idea is the sample is going to represent the population and allow us to draw conclusions using this. Now, that brings up sort of the first issue with how we do statistics. We're now using a sample to represent a population, which means that our sample might be biased or different than the population that it's actually representing. So we've included some inherent variability in there, or error. So what can we do about this? Well, we can look at how likely the results are given the sample we use to represent the population. And that's sort of how p-values came about. So null hypothesis testing framework itself is sort of a mashup or an alliance of two different sort of ideas when statistics were sort of starting to be populated throughout most of the applied sciences. The first is Neyman and Pearson developed hypothesis testing along with type 1 and type 2 errors. And their idea was you could define an error rate a priori, which would give you a critical statistic based on a distribution. Then you could compare your observed value to that. And if you did this over and over again, you'd be able to define type 1 and type 2 errors as well as what's significant. In sort of a competing camp or parallel camp, R.A. Fisher developed p-values. And these were designed to be a continuous metric for assessing strength of the outcome relative to a null hypothesis. Now, these two things have sort of been combined for ease, and it's sort of awkward to talk about, terrible to teach to undergrads, hard to teach to graduate students, and hard even to this day for people to understand. A lot of times when you're talking about like the null hypothesis test, it can get really tricky when you're talking about wording for some things. But essentially what happened was people didn't want to have to replicate the experiment over and over again using the Pearson-Neyman method. But what you could do is you could take the p-value from Fisher, because that was a one-study thing, and then add it to this or that conclusion from the null hypothesis testing. And that's sort of where we ended up. It does seem to work in that science does seem to continually advance and improve. But always keep in the back of your mind that we could probably be doing things better. So here is the famous confusion matrix that we always show individuals. And this is, again, just for sort of definitional purposes. You'll see the columns are reality. And that is, we have whether H null is true. So that's on the right side. That is, there's no effect in the population. On the left side, we have there is an effect. And then you'll see that your study, because we're sort of adopting this null hypothesis framework, will come to a yes or no answer, or this or that, and that is we're either going to reject or fail to reject. And when we reject and the null hypothesis is false, that's a correct decision. When the null hypothesis is true and we fail to reject, that is also a correct decision. So you want to stay on the diagonal. On the off diagonal, we have our two errors. The first is the alpha, or type 1 error, and that's rejecting a null hypothesis that is true. The alpha level, or level of significance, is a probability value that's used to define what's very unlikely. And in the other off diagonal, I know it's weird to talk about diagonals in a 2x2 matrix because everything's diagonal, but if you're used to talking about matrices in math, this is what happens. The type 2 error is failing to reject a false null hypothesis. That is, you didn't find your effect when you should have, or it does exist. So you'll see in that previous slide, I had sort of an asterisk next to p-value, probability value, because let's talk about that right now. So what is a p-value? Here's probably the only time that I'll be super technical in my definitions. It's the probability of obtaining the results seen, or one's more extreme, given the null hypothesis is true, due to random sampling error. Now, I know this is like a bunch of weird concepts to join together. The important one, I think, and the one that I think is most often glossed over, is this is only dealing with random sampling error. The p-value tells you nothing about anything else. It is just the fact that we're using a sample to represent a population. So how do we quantify that? Well, we have adopted this idea of a sampling distribution, which is a hypothetical distribution for statistics itself. So the classic example is you take a sample, you calculate the mean, you mark it down. You take another sample the same size, you get the mean, you mark it down. And that new distribution of everything you've recorded is the sampling distribution. And if you get the standard deviation of that, that's your standard error of the mean. And so that's sort of how we talk about what the sampling distribution is. It's hypothetical because you're never going to repeat that all the time. When we're using significance testing, we compare our observed value relative to the standard error to see how different it is. That is, it gives us an estimate of sort of unlikelihood. Now, I know I understand that went through a lot of this really quickly. There are a lot of misconceptions about p-values, and they leave a lot of things to be desired, and I just want to cover a couple, and I realize this is sort of an aside from talking about power, but if you had read the articles that were sent around, you'll note that this is a big concept in the world of applied sciences. Probably since like 2010, it's been still mentioned. So, p-values do not indicate a degree of significance. That is, smaller ones don't mean your effect was stronger or larger. There is no such thing as marginal significance or trending towards significance. I always just ask people, how do you know it's not going the other way? P-values are not probabilities about the alternative hypothesis. They're probabilities about a specific data's null hypothesis. And I'll talk more about this in a moment. Also, your P observed is not your alpha observed. So that is, if your p-value is 0.034, you can't say there's a 3.4% chance of concluding the effect when there's not. Now, I want to talk sort of more about that misunderstanding about the probability value being associated with the alternative hypothesis. It's sort of so common that we have it named as the fallacy of the transposed conditional, and this is the exemplar example of why you would not want to do this. The probability of the data yielding the result seen, given the null is true, is not equal to the probability of the null being true given the result of the data. So again, p-values are the former, that is, how likely is this result given this sample comes from a population where the null hypothesis is true. So you'll see that in that definition, there is nothing about the alternative hypothesis. If you want to get to this, and you guys will talk about this later, you can sort of do it through Bayes. And so look forward to that, whoever's giving that talk. I will say this is sort of the one time that I have like a question, but given that we're recording and muting, I won't have anybody chime in. I'll just get right to the answer. But do people know why we use 0.05 for alpha? So eventually, when you sort of follow the path back, most people end up at the Fisher statement in a book in 1925. The value for which p, 0.05, or 1 in 20 is 1.96, or nearly 2. It's convenient to take this point as a limit in judging whether a deviation is considered to be significant or not. Deviations exceeding twice the standard deviation are thus formally regarded as significant. So, like, all of 0.05 essentially goes back to this. Now, the amusing thing is, in the same exact book, in fact, just a couple pages later, he says this: if 1 in 20 does not seem high enough, right, we might prefer to draw the line at 1 in 50 or 1 in 100. Personally, the writer prefers to set a low standard of significance at the 5% point and ignore all results which fail to reach this level. A scientific fact should be regarded as experimentally established only if a properly designed experiment rarely fails to give this level of significance. So even when we go all the way back to YP05, in the same manuscript or same book, Fisher is telling us don't always use P05, right? But we have just accepted this sort of as the nominal level across science. The other thing I want to point out here is the bolded sentence. And the fact that he says rarely fails, and this is implying that you're repeatedly doing it. So there's repetition or replication being done. There's no one study that's going to definitively come to a conclusion. So now let's talk about significance itself. Conceptually, how likely are these results given the sample we have that represent a population, and what is meant by only random sampling error? It's important to note what's not included in sampling error. And I cannot, like, if you took an intro statistics course with, I have like a whole lecture about this. This does not include any systematic bias at all. So if you're using p-values and the study was designed poorly, or there was an error, or there's experimenter bias, or there's data manipulation, including p-hacking, sampling errors, wrong statistical model, none of that is included in what significance testing is. Therefore, the p-value can never correct for any of these mistakes. So to continue to use just p-values without anything else supplementing it means we are glossing over a lot of these things because we don't talk about them, right? The p-value is just random error due to the fact that we took a sample to represent a population. Now, some people will tell you that confidence intervals are sort of the solution to this. I will tell you that is not the case. Because if you do them properly, they will always come to the same exact conclusion that your test for the p-value will be. So they are one-to-one. Some people will tell you that confidence intervals contain more information. And I will say, yes, if you're only reporting the p-value. You know what you could do is just report the results properly. And then you don't have to worry about this. So that is, we should always include the test statistic, the p-value, and the effect size, provided the effect size exists. And we'll get to that in a little bit. If the test is about a specific parameter or a relationship or a path, then the point estimate and its standard error should always be included. If you report results like this, confidence intervals add no further information. And in fact, this is always sufficient and for reporting what we would talk about as standard science today. So now let's move back closer to what we have been talking about, which is power and effect size. And you'll see that they go hand in hand, especially when you're doing power calculations. So the first question is, what is power? And I'll just tell you to ask a philosopher because I have no idea. And what is statistical power? Again, I'm an applied statistician. I am not a theoretical statistician. Ask a philosopher of science, please. What we can do is mathematically, right, define what power is. And that's 1 minus beta. This is the proportion of time you are not committing a type 2 error. Now, it also feels really weird to define something as what it's not, right? And this is probably not great practice in science. I also want to say that textbooks and intro often say power is the ability to find an effect given it exists. Again, that's not really comprehensive enough. And you'll learn this the first time you want to show that two things are not different from each other, right? Where the null hypothesis is now the alternative hypothesis from what was before. And so this failing to find an effect that exists is not expansive enough. This also sort of happens when you're looking at model fit. So how I define power and sort of the again, because I'm a statistician, right? I qualify everything so that like in the future it can't be held against me. In the context of hypothesis testing in statistics, this is how I would define power, right? It's the pre-study ability or probability, if you want to put it into a metric, to detect a correct alternative hypothesis. And so this sort of Ryan made up definition, right, is expansive enough to cover almost all of the research that you guys will be doing. Now, I will be straight with you. This doesn't always cover AI and exploratory analyses, right? So I just want to make sure, again, the statistician in me is like always qualify, like you can't be wrong in the future if you just make these things known. And the idea of my definition is Does your study show support for your scientific hypothesis? Which goes back to that thing I've talked about on the very first slide. Now, the one question that everybody seems to agree on is, why is power important for research? And it's basically because we don't want to fund a study that's unable to draw a conclusion. Right? It's a waste of time, effort, and resources if you run something and you can't come to a conclusion. So what do you need when you're going to look for power? Well, it's a combination of different concepts, which we sort of talked about here. The first is we're now have drafted the use of p-values in null hypothesis testing, and this is like where some of the chocolate mess comes from. But for actually calculating power, what do you need? So you need an alpha or significance level. Now, in a basic intro course, they'll also talk about a non-directional and a directional test. I'm just going to lump them in with significance because what you're really doing is just saying whether your alpha is all in one tail or not, and it's just moving the critical values or moving the region of significance to be smaller. You also need to choose the right statistical model or test. You need to determine a sample size and an effect size. Using all of these things, you can then find power. So what happens in practice? Well, typically, we fix two of the three main things, which is the power, the sample, and the effect size, and we find the other one. We've sort of adopted alpha 05, again, just because that's what people read first in the book, maybe, as opposed to reading the sentence second. And then sample and effect size are sort of the other complementing pieces for when you're doing a power analysis. Sorry, so it just comes up when people put in chat. So are there questions that I should pause for, Keith?
Oh, no, sorry, Ryan, you're good. I was just adding some links to other terms on things you were
Oh,
saying. So,
perfect. Sorry, thank you.
no, you're good.
So let's talk about effect size for a moment. And I think that reporting effect sizes supplement one of the main weaknesses in p-values and why I am all for making people report them when they exist. So p-values are sample size dependent. That is, you can just continue to increase your sample size and you can find significance. What it doesn't tell you is the absolute amount of effect or how much practical meaning that has. They also only account for random error, not systematic bias or poor methodology. So effect sizes specifically are designed to not be sample size dependent. That is, they want to tell you the magnitude of the relationship, not whether it's been due to chance. So you can see how these two things complement each other. I'm going to include a link here. This is a wonderful site for finding out about effect sizes as well as calculating them. And a lot of them have sort of an applet that you can actually just use on the website. This is sort of the most comprehensive one I've found and I use. So what do I mean by p-values are sample size dependent? So imagine an outcome that's normally distributed with a mean of 50, and here I'm going to say it's a standard deviation of 10, even though technically, right, we would say that that's the variance value in those. We want to use a z-test to see if an intervention increased scores. We're going to define our alpha, it's non-directional, therefore our critical value is 1.96. Here's scenario A. We take a sample of 25, we obtain a mean of 53, so we can get our standard error really easily because these made up examples mean that I don't have to worry about math, right? So we're just looking at to get the square root of n, so the square root of 25 is 5, put the 10 over 5, and we get 2. So our standard error is 2, and you can see the difference in the mean value from the expected distribution, right? 50 is 53. So we would put that effect over the standard error, and that gives us our z observed. So 1.5. You can also calculate the Cohen's d for that, which is simply 0.3, which is removing the influence of sample size. So you'll see it is literally just the mean difference over the deviation. You'll see that for a sample size of 25 given 53 was not significant. Now, an alternative scenario. We sample 100 individuals. We obtain a mean of 52. So now the effect is smaller, but we have more people. So what happens? Well, again, you go through, you see that the standard error is now 1, and you can see that 2 over 1 is 2. Our z value is 2. It's now significant. So the effect size is weaker in the second one than the first scenario. All we did was increase size, and now we have quote unquote significance. If you were to report the p-values with the effect sizes for both of these studies, the effect sizes would tell you more of what's going on than the p-values. The other thing that happens when we just inflate n is that we typically reduce variability, which means that we can also reduce errors sort of in the math of the back end. So it's like an added bonus of just increasing your sample size along with trying to get significance. And then you would ask me, so in theory, if we just continue to increase sample size and you find significance, does that mean that your finding is real? And taking the statistician cop out, maybe. So it could be that the effect is really small and you do need a really large population to find it. Or it could be that you just kept inflating the sample size, and you found something that's not really important and significant now. So what are some common effect sizes? And again, like, I cannot stress enough that everybody should be reporting effect sizes for everything they do. So when you're doing general linear modeling, think regression, ANOVA, right? ANCOVA, mixed design ANOVAs, all those things that you're familiar with from a linear modeling course. You have Cohen's d for means. When you get more than 2 means, you can use the partial eta squared or Cohen's f or f squared or omega squared. When you're using sort of a regression model, you might think about reporting r squared or the change in r squared. When you're looking at subsequent model fit, that is adding predictors to a model and seeing if that increases model fit or they are significant. Also, adjusted r squared, which is nice because it sort of tweaks the r squared based on your sample size and the number of predictors. How about when we move to generalized linear models? Well, there are pseudo r squared measures, but those are based on the likelihood. So you can't say things like, well, we accounted for this percent of the variance, because that percent of the variance doesn't exist when you're doing those sort of calculations. But you could say it relative to a likelihood, how much have we accounted for? And sort of the popular one would be Nagelkerke's r squared, which is one you might see the most. Also, when you're doing some of the generalized linear models, depending on the link function you choose, you can get an effect size for some of the actual parameters for the estimates, so slopes, right? And you get an odd ratio with the logit or relative risk with the log function. AIC and BIC are information criteria, so that's Akicki's and Bayesian information criteria. And these are sort of taking a likelihood value and applying corrections for how many predictors are in a model. Now, they're not useful on their own, but they are useful for comparing models to each other. Instructional equation modeling, that we have absolute, relative, and incremental fit indices. And in fact, I would tell you that if you are reporting SEM results at the model level, but you should probably report one of each of these, is how I would suggest it. It's a little bit different when we have a model that roughly fits and we want to test a specific path within that. That's sort of a different sort of research question. Because again, you can go to like a standardized slope or something like that. Now, the sort of one that's out in left field that's causing the most sort of wishy-washiness in sort of applied methods moving forward, which is what do we do with mixed models? Well, for the random components, the ICC exists, and that seems to be generally relatively acceptable as pretty good. And that's the interclass correlation coefficient. That is how much variability is accounted for by the random components in the model. What we don't have is something that's analogous for the fixed effects. So, I'll talk about two common ones. The first one is a pseudo R squared, which is you run the model, you save your residuals, You run the model without the effect, you save your residuals, and you look at the relative difference in the reduction in the error variance between those two models. Now, this comes with a lot of caveats. It's almost always really small, and it doesn't exist for some instances. So the common one that happens is you have an RCT, you have multiple groups, multiple time points. In that analysis, we have a main affected group, a main affected time, and the interaction. This pseudo R squared can be found for the interaction. It cannot be found for the main effects when the interaction is in the model. So therefore, it always requires a note from me to the editor saying this doesn't exist for those. Now, one sort of newer one that I sort of just saw this summer, and I'm not going to try and pronounce a name, so I apologize to both of those authors. They just call it F squared. I'm calling it a generalized pseudo F squared because I don't know how else to frame it. And it is calculating F squared just from the fixed effects in the model. So ignoring all the random components. I'll be honest, I don't know how I feel about this. It's sort of new enough that nobody's really adopted this. One thing I will hope is that in the future, someone's able to rescale this based on something from the random components aspect. Now, again, you're going to have to get a theoretical statistician that's good at math to come up with that formula. But there are now no excuses not to have at least something reported for mixed models.
Ryan, can I actually interrupt you there?
Yeah.
I think this slide has generated a lot of good comments in the chat,
Oh, sure.
and there may be some things I think we can get into more in the Q&A. But to synthesize some of the comments here, I think one thing is with effect sizes, it's super contextual, right? And so you for different kinds of analyses, you get very different types of effect sizes. Um, so, what do you have any recommendations on, I guess, being general? Like, because I feel like one thing I always think of is just sharing your data solves a lot of problems because then people could just go calculate whatever number they actually want. So if you can do that, that's good. But maybe if you could comment more on like if I have to report a Cohen's d versus a partial eta squared or just like the raw means, like what do you how do you kind of think about that?
Yeah. So, and it's funny that you mentioned this. Is like we did not plan this, but we will talk in a moment about how you can translate those. So like a D can be converted into a partial eta squared into an F squared. And how I always sort of perform my power analysis with that in mind. So that's, thank you for leading right there, Keith. The other thing so this is what I do with students is when you're writing up your results, report your effect size and then place it in a sentence in context. So you would say, my regression model predicting Y with these X's, adjusting for these covariates, right, can account for this percent of the variance. Now, that's a little bit different when we're talking about a partial eta squared. People don't need to worry about the math. The denominator is slightly different. But think of it as an R squared for just the effect and an error. So that is sort of in isolation. What would that's like an R squared that way. Obviously, Cohen's d is like the universal one that people understand the easiest. And again, you'll see in a little bit, like I just convert everything to a D when I put grants in because that's what people know, right? It's not necessarily best practice, and you can't do it all of the time, but whenever I can, that's what I do. Any other sort of follow-up questions there?
No, that's great. Let's let you keep going, and then I think if people have other things, they can bring it up in the Q&A.
Perfect. So how do I think about where do I fit right in the research process? And like you talk to a statistician and like we want to be involved up front and at every stage, or at least I should say the good collaborative statisticians want to be involved up front and at every stage. And so here's sort of in my mind how the process goes forward, which is, people come to you with an aims and a design in mind, right? And those two things sort of feed back to each other. Using that, we talk, their aims get operationalized, which gives you the measures. Given your design and your measures and your aims, you can pick a model, and that leads you to an analysis plan, which then allows you to calculate power. So if anybody here, I saw a couple people that are familiar, if they remember working with me, the first thing I do is I make people operationalize all of their measures for what we're talking about. And I will ask relentlessly, how are we measuring that? What does that mean, right? And so I start upfront with aims with people. Part of that is there are a couple things people do that are like easy that I dislike. One is the outcome determines the model. I don't want to be in that mindset. First of all, a lot of times your outcomes can actually be transformed. So if you take something like falls, right? Say you're tracking falls over a year. Well, you can have a fall or not faller, right? So now you have a dichotomous outcome. You could do the sum of falls. Well, it could be, right, that approximates a normal distribution if you have lots of falling. Well, it could be a zero inflated if you have nobody falls. And so your outcome itself cannot pick the model that's most appropriate because you don't really know what it's going to be yet. Only using models the researcher is familiar with. Now, I will say that when I go to people, I always start with what they're familiar with and then try and bring them to the level or the method, the model that is most appropriate. The other thing I hate is, oh, well, everybody in my field uses this. And it's like, I don't care what people in your field use. There's a better way to do it. The other thing I will say is I dislike when people use overly complicated methods to try and influence the innovation. And you will see that like, well, why are you using this huge model with like a bunch of AI components or machine learning? And like you have a specific set hypothesis. You don't need that. And it's clearly, essentially in my mind, you're like gilding the lily, right? Because the statistics is like this minor component in the approach. And so trying to get that to cover something else that's a weakness is not going to help you. So then again, this is just me, like I hammer people with their aims and their hypotheses nonstop. I rewrite people's hypotheses so often. I always reframe their aims and then their hypotheses. So here's how I think, when I approach working with people that like, here's the logical flow. And again, I've been successful now that I can sort of force people onto this path. So, if you're relentless enough for good practice, it should work. Somewhere on your aims page, you should mention the design. Whether that's in the aims or above, it doesn't matter. And again, I'm talking about like, are you doing a clinical trial? Is it a pilot study? Is it a cohort study? Is it a retrospective review? Your aims language itself is sort of your sentence that's broadly speaking, sort of the content-wise, the construct level of what you want to do. And this is aimed at your significance, your innovation, and your impact statement. I have this, new intervention that's going to increase walking ability or something like that. And then when you get to your hypotheses, you're going to operationalize everything that you say. That is specifically what's being tested. What are your metrics? So your aim might be, I want to improve walking ability. Your hypothesis will be something like, compared to a control group, right? This new intervention from time point 1 to time point 2 will increase 6-minute walking distance or self-selected walking speed, right? So the aim itself is construct level. The hypothesis has been nailed down as much as possible. The reason I do this is if you read the aims and the hypothesis this way, and you know the design from somewhere on that page, you'll know immediately what statistical models are appropriate and sort of where you're living in the power realms. Now, I will say that I've probably submitted, probably 110 grants, and I've never once gotten feedback that my aims have been unclear or need to be rewritten. So until that happens, I'm going to continue to make people do this. Here are some sort of generic suggestions I have when working with people. And now this is like, I would tell statisticians this, but now I'm going directly to you guys to tell you this. Limit yourself to 2 or 3 aims. The most I've ever submitted is 4. If you do that, if you continually put more and more in there, you will lose focus and specificity, and then trying to explain every single one of the aims gets too cumbersome, and you lose sort of the overall impression in a grant. I tend to think of each aim as a separate research question. So that is, they'll each have their own alpha. Now, outcomes are a little different. I know everybody, and it still happens to this day, they come to me and, look, I have these 10 measures I want to put in my aim 1. And it's like, yeah, no, right? Like, it's one thing if you're doing exploratory analysis. Again, that's a different ballgame, but what we're talking about is sort of hypothesis-oriented incremental research where you want to validate, an actual hypothesis statement based on previous work. And so what I tell people is, let's narrow that down to 3. It could be less, it could be more, right? It's somewhere in that range. And then I will adjust alpha to account for 3 outcomes. And then I will have them list the rest as secondary. And we'll use just a much more conservative alpha for that. Now, oftentimes when you're talking to people, they have 10 outcomes because they have a functional measure they want to do, and there's 3 of those. And then they have, a psychological measure they want to do, and they have 3 of those. So I often found getting people to pick one of each of those is sort of the best way to do that, because then you're covering all of the domains that you want to cover, and you're still limiting yourself to be not alpha adjusted to that you're never going to find significance. Now, if you do have a model where you're doing a lot of comparisons, you may have to still, on top of alpha adjusting, apply a post hoc correction, which again shrinks your alpha down even more. So you do need to sort of be cognizant of how much you're doing. Here's something I always tell people to put in their grants. Have a section for additional analyses. Most of the time, in fact, I think every grant I've ever been worked on, people collect more data than exactly what's specified in the specific aims or for the hypotheses. Right? Use this as a selling point. Like, if you fund this work, we will be able to address these aims. Plus, we have all these other additional analyses that we could do with all of this data. And I feel like a compelling argument that was made to me when I first started was, these are a great way for pilot projects for new, or for getting effect size estimates for future studies. Another thing that you want to always have is an alternative approach. And that is, what if, the model that I was going to use in one of the aims fails? What am I going to do? Or not everybody agrees that this method is the best. So then I back it up with literally a section that will say alternative approaches. If this cluster analysis fails and nothing hangs together, if this mixture model fails and there's no, homogeneous subgroups, what are we going to do? Right? How do we address that? The other thing that I think, current administration notwithstanding, I believe that we do want to start to think about, sex is a relevant biological variable. There are probably a lot more that we should be thinking about that we don't. And this is a great way of always making people include that. Again, the researchers here are probably so used to including it that it's not going to not be on their radar. But for us that have started before that, we sometimes need to be reminded. The other thing that's sort of a red flag for me is when people put down a lot of advanced analyses and they never mention anything about the assumptions or follow-up tests. So it's like, as soon as you start to mention the assumptions that are needed and how they're going to be addressed when they're violated, or if something can be, changed method-wise, going back to the alternative approach, right? That shows me that the statistician has thought enough about what you're doing that he's probably part of the collaborative team. So now here's the part that everybody probably wanted me to get to, right? Been talking a while now. So how do I actually perform power analysis? The other thing is I feel like people are going to be really let down when they hear how this works. So I nail down everybody on their design, their aims, their hypotheses, and their measures. And that is, I literally have them say, and I won't run a power analysis until their aims and their hypothesis statements are worked out. I should add, as like a little aside, like power calculations are the worst part of my job, and so that's why I make everybody do all this stuff up front. Given all this, I do want to offer multiple methods or ways for people to analyze their data. And that is, so I'm constantly offering options, saying what's the benefit or the detriment to doing that one versus another one. The other thing, it really is helpful to have another person that knows a little bit about statistics, or, if you're lucky, you can get, somebody that's smart that knows a lot about statistics, and then you just constantly bounce ideas off each other. What's the worst thing that happens is the person comes back to you and says, hey, I would not have done that. And then you've caught the mistake up front, right? The worst thing that happens is they don't have any comment, and then then you can feel good about yourself because then you nailed it on the first try. So here is like the most important thing that happens. After I nail down the design and the aims and the measures, I look at the PI and I say, what can you afford to do? Right? And that is literally how power is found in almost all of the work I do. That is, given the money you're asking for and the time you have and your resources, how many people can you include in the study? After you get that number, then you need to look at them and be like, is that including dropout or pre-dropout? Because oftentimes people are not thinking about that up front. Again, I'm using dropout casually here to be literal dropout for longitudinal work, as well as like error and missing data and all that sorts of things. So then whatever N they tell you, reduce it by the dropout amount or inflate it by what is needed. Confirm they're okay with that. And that is, just make sure that, like, I've come to this word completers. So that is like, here's your target for completing the study with full data. That's what we're powering for. You will mention how many people need to be recruited or screened for to get to that. So here's step 2 is estimation. I set alpha at 0.5, power at 0.8, because these are sort of the nominal in the field, and that's what people expect. Oftentimes you have to adjust alpha for, if you have multiple primary outcomes, right? So I would adjust there. The other thing is, if you're using within subject design, you will want to account for the correlation among repeated measures. I almost always use the compound symmetry or the Lear, which is sort of like an autoregressive approach. So the reason for using those is, one, everybody knows or familiar with them, and most of the models are able to account for them. I then calculate and estimate the effect size that can be detected using the model we've picked out with the N they've given me with alpha 0.5 and power 0.8, right? So people always come to me and like, what's the sample size I need? And it's like, let's not find a sample size you need. Let's find the effect size you can find with the people that you can afford, right? Is the number one thing that I say to people. Now, how do I actually do this? So I convert everything to a z-score metric and then run my power analyses this way. Now, the idea here is that most of the softwares will let you scale variance in ways. And so by doing this, your effect is always sort of immediately comprehensible to the people you're working with. And also, when you're using a standard deviation of 1, you don't have to worry about all the weird things that can happen when you're actually putting in random values or observed values for deviations. Then what I do is, after I find the value, I convert it into whatever effect size is most appropriate, whether that's f, f squared, r squared, d, partial eta squared. Now, when I say what do I mean, let me explain a little bit about what do I mean by putting in a z-score. So imagine I'm comparing two groups over 3 time points. Well, I'll just set the baseline value as 0. Let's say the control group is going to increase scores. they're going to increase by half a standard deviation across these time points. So from 0 to time 3, that's 0.5 deviations. Now it's easy to talk about the change in the intervention group relative to that. Say they change the full standard deviation. Well, that's really easy to look at the Cohen's D for, right? Because that's a half standard deviation stronger than the control group. So my D was 0.5. Right? And so the other, sorry, I have this other thing. Like that's, if you convert it, and I'll go through in a little bit of how you would convert it. The important thing is, no matter what the outcome is, this applies. I don't know, maybe the second grant I worked on, I was doing it the way that people would have traditionally taught you, which is you get an estimate of variability from the people from the literature or from a pilot study. And then we got to like a week before the grant was due and they changed their outcome. And it was like, oh, all those calculations, I have to redo all of them. Well, you know what you don't have to redo? You don't have to redo it when it's based on a standardized effect size, because then you can just convert it back into whatever metric they want. The sort of the last little piece of this is, so they gave me the N. I had the standardized values for alpha and power. I've now calculated the effect they can find significant with that N. And then I go back to them and be like, hey, is this reasonable? Does this make sense? And by reasonable, I mean sort of a two-pronged thing here. One, is that obtainable? Is that, can your research actually make that change? Along with, is it clinically meaningful? Is it relevant? And that is, can you check the literature for MDCs, MDICs? I will share my slides for Keith to pass around at the end. There's a bunch of different things. I have included a bunch of example statements from grants I have submitted, so people can sort of parallel that. So what do I use for these? And I don't know if do we need to take a pause here, Keith? Am I going too long?
Yeah, we are coming up on time for the first part, but I think maybe just one clarifying question too, Ryan, and listening to your approach. So other terms that people might be aware of. I think kind of the traditional method would be an a priori power calculation. And your approach is more like what some people would refer to as sensitivity analysis, right?
Yes,
Is
exactly.
that okay? Yeah. So if
Yeah.
people are interested in searching on some of these terms, that might be sensitivity versus a priori power.
So I don't have too many more slides, thankfully. Everybody will be happy. So what do I use? So G-Power, it's free but sort of limited. Now it's great for graduate students and first starting. I will say Glimpsy, was like an early adopter of Glimpsy, like the first year it came out, when it was still like samplesizeshop.org from Florida. That's great for mixed models. Again, that's free. The power and sample size is good. The downside of the end, that's a computer package that you have to buy. It also can be a little clunky. The nice thing about using like a Glimpsy or a Pass or a G-Power is they're validated tools. The other link I have here is for the effect size conversion, and this is the spreadsheet that allows you to convert all those effect sizes to each other. If you're looking for mediation, here's a Shiny app that I use a lot. For SEM model fit, there's sort of 3 different ways to go about it. Onyx is a great one, Power SEM and R, or just using sort of a simulation in M+. Which brings me to the last thing, is like, how often do you use simulations? And it's like, not often. Do you know why? Because I don't have time. The other thing is, oftentimes simulations have a lot of hidden assumptions that you don't think about up front. So even like you're going to do something like a simulation for regression, and then it's like, well, how related are the covariates with the outcome? And it's like, I'm not in your field. I can't make that assumption. How strongly are the covariates related to each other? Right? Again, I'm not in your field. I don't know these answers. And emailing them every time you have a question gets onerous for people. So while I do use simulations, they tend to just not happen in reality. The other thing people will say is reviewers will often comment on missing this. And so I'm of the sort of stance that if you're using maximum likelihood, you're already accounting for missing data because it's a full information, and that is you're using the data that is present. And I sort of contrast that with what I think is the best way of imputation currently, which is multiple imputation using the EM algorithm. ML is just sort of better. So what happens is in multiple imputation, if you can do infinite imputations, you will estimate essentially the same answer as using maximum likelihood up front. So I'm not a fan of imputing data. I would prefer to use maximum likelihood. The other thing that the imputation can lead to is a whole bunch of other decisions that you have to make a priori, which is choosing the method, the prior, the number of times you're going to do it. Also, imputation might have a model for imputing that's different than analysis. And again, explaining that to people can be convoluted. The other thing, and I just want to make sure everybody's clear on this, that means your statistician doesn't have to run the analysis multiple times and combine the answers. There's a small set of slides walking through details again that I'll share. And so here's sort of just like my comprehensive overall perspectives on this. Power itself, like the a priori power that Keith mentioned, is sort of overrated in a sense. I'm much more practical in that give me the n you can afford, let's find the effect size that you can get with that. Is that realistic? I will say that it does keep us employed, so please keep using statisticians. The other thing that people really don't talk about is that power is a probability. So that is, everything go according to plan. That is, your effect size is large enough, you've gathered the appropriate sample size, and your study might come out not significant. Well, that's because power is set to a value. It's never 100%. And so if we use the nominal level of 0.8, 1 in 5 studies that are fully powered that reach the effect size they wanted to will not be significant. That is not your statistician's fault, okay, people? Because I've had this conversation before. The other thing I think people lose sight of when they're talking about sample size calculations is that the representative of your sample is more important than your sample size. That is, how well does your sample represent the population of interest is more important than raw size. And again, this goes both ways. Like if you tell me you're fully powered with an N of 10, I will tell you to go back and come up with a better sample size. And here's the other sort of soapbox things that I have in mind. For the life of me, I don't understand why we have to include all the statistical information in the approach section. Please just let us have our own little thing at the back end where we can explain everything without PIs chopping all our words in half and reducing our size, right? We already do this for other things. This is easy. When all the people here get into power, please think about this change. The other thing that is like, I'm getting old now, right? Confidence intervals are not the solution to p-hacking, right? Make people report results correctly. And again, at the back end of the slides, I have how you should properly report a bunch of common models. The other thing, and he sort of lightly touched on this before, is sometimes just having your descriptive information in there can be enough for readers to get the message. You know, my mean reduced by this much, or it increased by this much. And if I show you both those values, you are able to tell me as an expert in the field whether that's meaningful. Don't ever calculate post hoc power. I have a reference that says that it's foolish. Here's what post hoc power tells you. If it was significant, you had power. And if it's not significant, you don't have power. Literally, that's what's going to happen every single time. The other sort of minor soapbox thing I have is, I don't know why we require power for pilot feasibility and student dissertations. Like, these are students working on small projects, people. They are not doing an R01 in 1 or 2 years. Please let them have a slightly underpowered study so that their first R01 can be the fully powered one. And then this sort of goes back to the replication stuff I said up front. I don't think any one study is able to draw a causal conclusion. And so I always think it's replication. So stop trying to power a perfect study. It's much better to have multiple replicated smaller studies than one huge study that's trying to accomplish everything. And then my last tiny little soapbox thing is I don't know when meta analysis became better than RCTs in like Cochrane and stuff. I don't understand why this would be the case because a meta analysis on observational studies is going to be inferior to a good RCT. So there's this Hopkins approach, and that's the link here, which removes meta analysis from that hierarchy of evidence and sticks it in with what is the meta analysis made up of. So if it's a meta analysis of RCTs, yes, that's as good as RCTs. It's a meta analysis of just observational studies. It's probably better than just observational studies, but it's not as good as one as RCTs. And then, so the rest of the slides are just references and a bunch of examples and stuff. And I apologize for going over and for running at the end.
No, that's perfect. Thanks, Ryan. You also, we gave you a big ask with covering such foundational content, but I appreciate you getting through it and also setting the stage for a whole bunch of other things that we're going to try to touch on in subsequent sessions. So I want to shift over to the Q&A because I'm sure people have a lot of great questions for Ryan. Just before I do, for anyone who does need to go, please feel free to scan the QR code here. You can leave us feedback on the webinar. I'll bring this up again at the end of the Q&A session. And I'll plug our next webinar in this series, which will be on Thursday, February 19th, with Kristen Sanani from Stanford University, where we'll be talking a little bit more about kind of aligning your hypothesis with the study design. And really, those are you trying to design for superiority, non-inferiority, or equivalence? And all those things kind of require slightly different considerations. So just giving everyone a chance to scan that QR code if you do have to jump off. And otherwise, I will stop the recording.